Bom, agora estamos ao vivo. Good morning, everybody, and thank you so much, Marcelo Pavanello, for sharing your knowledge with us. We thank you so much for the time and effort take for giving this talk to us, to our chapter. It's a distinguished lecture of the IEEE Electron Devices Society. Marcelo Pavanello is a full professor at the Electrical Engineering Department of Centro Universitário FEI. His current interests are the compact modeling, fabrication, electrical characterization, and simulation of SOI CMOS transistors with multiple gate configuration and silicon nanowires. The wide temperature range of operation of semiconductor devices, the digital and analog operation of novel channel engineered SOI devices and circuits. He is the author or co-author of more than 400 technical papers in peer-reviewed journals and conferences, and the author-editor of 6 books. Dr. Pavanello is a researcher associated with the National Council for Scientific Development, CNPq, Brazil, a senior member of the IEEE, and a member of the Brazilian Microelectronics Society. Since 2019, he is an editor of the IEEE Transactions on Electron Devices journal for the topic Process and Device Modeling. Since 2021, he is an editor of the IEEE Access journal. Since 2007, he serves as IEEE Electron Device Society's distinguished lecturer and has been nominated to the Compact Modeling Technical Committee of the IEEE Electron Devices Society between 2018 and 2021. In 2008, he has been with UCL as a visiting professor. Between 2010 and 2020, he also served as vice rector for teaching and research at FEI. Dr. Pavanello coordinated several research projects fomented by Brazilian agents like FAPESP, CNPq, and Qbits. He also supervised several PhD dissertations, master theses, and undergraduate projects in electrical engineering. Dr. Pavanello received an electrical engineering degree from FEI University in 1993, receiving the award Instituto de Engenharia, given for the best student among all the modalities of engineering programs offered at FEI. He received the master's and PhD degrees in 1996 and 2000, respectively, in electrical engineering from the University of São Paulo, Brazil. From August to December 1998, he was with Laboratoire de Microélectronique from the Université Catholique de Louvain in Belgium, working in the fabrication and electrical characterization of novel channel engineered Silicon-On-Insulator transistors. From 2000 to 2002, he was with the Center of Semiconductor Components and Nanotechnology, State University of Campinas in Brazil, where he worked as postdoctoral researcher in the development of a CMOS NOL process. In 2003, he joined FEI University. So thank you very much, Marcelo. And during the talk, you can type, for the ones that are following over YouTube, you can type your questions in the YouTube chat, and I'm going to read them to Marcelo Pavanello at the end of the talk. So thank you very much, Marcelo. The floor is yours.
Thank you so much.
Thank you, Marcelo.
Thank you so much, Gilson, for your kind invitation and for your kind introduction. Good morning to you all. Good afternoon or good evening, depending on where you are in this over the globe. Well, it is my pleasure to be with you in this morning to talk a bit on my work developed along the past few years on cryogenic operation of planar and multi-gate fully depleted SOI MOSFETs. Well, this is a pleasure for me to join you in the chapter you recently created at the Federal University of Rio Grande do Sul. It is very nice. We have this new chapter in Brazil, and this is a very active one. Then I would like to congratulate you all for the very nice work you are doing there in this electron devices chapter, joint electron device chapter. This presentation, as Gilson told in the beginning, is a part of the Distinguished Lecturer Program from the IEEE-EDS Electron Device Society. And well, I think it's not necessary to go further in the relevance of being associated with a worldwide society like IEEE, and the amount of information it can provide us as engineers, researchers. Well, it can give us access to state-of-art information. And then, of course, one of the benefits of giving this access is also to be integrated in the research world. And you have a long list of presentations in your chapter with a very large number of researchers from different topics, different aspects, and all of that. Very much thanks to the electron devices, the Distinguished Lecturer Program. So with no further delay, I want to give you this outline during this morning, but I'm not so strictly close to this set of points. So depending on how we manage the time, we may talk on a few on some aspects or further in other aspects, depending on your interests. So if you want, instead of Gilson told you in the beginning that the questions could be made in the end of the presentation, if you have some specific aspect that you would like to have an additional comment, do not hesitate to type your question for Gilson during the presentation, and Gilson can pass the question ahead, and then I can stop and start answering your question or commenting on that. This is I want to do this presentation in a very relaxed way. Okay. Well. So we will talk about SOI nanowires, about stacked nanowires, and planar SOI MOSFETs. So what is common for all these devices is the SOI aspect here, and the SOI stands for Silicon-On-Insulator. So all these devices we present to you in this morning are made on Silicon-On-Insulator substrates, which I mean, they have a very thin silicon layer over an insulator layer. So schematically, you have an insulator layer of SiO2, and then you have a thin layer of silicon, or depending on the case, silicon germanium. The thickness of this layer is in the order of 10 nanometers. And the thickness of this boron oxide that isolates the active silicon region to the substrate itself. So the substrate contact is, let's say, here. The thickness of this region is, as I told you, in the order of 10 nanometers or so, or smaller, or thinner, sorry. And the thickness of this boron oxide can change from 120 and 145 nanometers down to 25 nowadays, depending on the technology, especially the planar ones. This thickness is being very much reduced. What is common in all these devices, additionally to the substrate, is that we will be talking about their operation in cryogenic environments. So I will focus my attention on their electrical characteristics in cryogenic environments. Most of the data I will present you are experimental ones and made from technical analysis on these experimental data, but we also developed some compact models and so on, but I do not include these data in this presentation for the sake of time. Okay, so backwards, instead of acknowledging everybody in the end of the presentation, I will start thanking people who collaborated with me to build up these works. So, because at the end of the presentation, nobody is anymore paying attention, so I decided, I saw in a presentation, this is not my invention. I saw it in another presentation and thought it would be nice. So I would like to thank Professor Michele de Souza and my students. I will not nominate all of them, but they are all here from FEI, which are working with me in the development of these topics. I would like to talk the colleagues from CLT in France, Jean-Pierre Collange, Maud Vinet, Michael Cassé, Olivier Feyneau, Sylvain Barrault, and Flavio Bergamaschi, which work in which we have with them, we have a very straight collaboration, and they provide some of our devices, and we have a long collaboration all over the time. With the Institut Neo in Grenoble also, we have Bruna Cardoso Paz, which is also a former PhD student from our university. From Sinvestava in Mexico, we have the partnership with Antonio Cerdeira and Magali Estrada, and in Federal University of ABC, we have Renan Trefisoli. So with these people, we work in quite close connection, and we developed most of the work I'm going to present to you. And of course, with no money, we can do nothing. So I want to thank the agencies that are funding our works, especially the Brazilian agencies, CAPES, CNPq, and FAPESP, and also the joint alliance of IBM, ST Microelectronics, and CLT, which also sponsored indirectly our projects, providing samples. Okay, with no further delay, let me then go to the introduction and the main ideas I'm going to cover. As I told you, I don't want to be so straight with the outline, so if you want to stop me anytime, do not hesitate. Well, nowadays, multi-gate transistors are one of the main enablers for the continuation of the MOSFET scaling. The multi-gate devices reached the maturity for mass production, and they are nowadays on the most advanced products. And just to illustrate it, I have here some pictures took from Intel, where you see some FinFETs. These are the third generation of FinFETs, and well, they say this may be for the 10 nanometer technology, but in FinFETs, what you see is a tall device and narrow one. So you see, evolving the technological nodes, they become tall and narrow. Well, the reason for this device has been chosen for the most advanced technological nodes is associated to the improved electrostatics, the proximity of these two gates. So here it works more like a double gate device. So you have one gate in this side and the other gate in this side. And then here you have the silicon, and the silicon is then being electrostatically controlled by decoupling between these two gates. So you can imagine the source of the device. So this is a cross-section view. The source of the device is on my side of the screen, and on my side, and the drain of the device is on the screen. Okay, so these are, as I already told, these devices reached maturity for mass production. But what comes next? What are the enablers for the next technology nodes within the nanometric length or within the nanometric range? So one of these ideas can be taken from this slide. This slide came from IRDS 2020. So you can see the evolution of the devices, and you can see here the FinFETs, but you start looking at gate-all-around devices, but the FinFET is still present, okay? And then if you go further to newer technological nodes, you start looking at stacked devices. You start looking at devices one on top of the other. And these stacked devices, we will talk slightly in this presentation, but these devices are in development by most companies. I can, for example, show you examples from IMEC, and here you see two devices stacked. So this is a cross-section view of what they call, or generally the industries are calling, nanosheets, but they can also be called nanowires. And the sense is because the idea is here is the silicon, here is the silicon. This darker part is associated with the gate dielectrics and gate metal, and this gray region over here, light gray, is associated with the silicon dioxide, and these devices are controlled by the same, they share the same gate electrode. Once again, this is a cross-section view, and these devices operate like a single transistor instead of being several layers of silicon. So these are the devices that are in development by most of the companies. This is an intermediate technological possibility given by IMEC or proposed by IMEC, what they call forksheet. And in these devices, you can see that MOSFET here is the silicon layer. So you see the silicon here, and here you can see the gate stack. So these are devices which operate in tri-gate mode. So you have one gate here, one gate here, one gate here, instead of the FinFETs I previously shown that have two main gates because they are tall and narrow. These devices are equally tall and narrow. Oh, that's why, because of that, these devices are being called nanowires. So I will go further in these devices during the presentation. So this is the roadmap given in last year by IMEC, their perspectives for the roadmap in CMOS technology. And once again, you see the continuation of the FinFETs, no matter the substrate, and the presence of stacked nanosheets from 2 nanometers for the 2 nanometer technological node and further. And maybe in the near future, or not so near, we will start looking at the complementary FETs, which are recently proposed and are associated with having the N FETs and the P FETs one over the other, one in top of the other, and they are working in close connection, minimizing the area and increasing the density of the circuits. But okay. So as I told you, there are nowadays several names for the same type of devices. I told you forksheet. I already told you nanosheet, stacked nanosheets, stacked nanowires, but all of them come with the same basic idea. We are having several nanowires, and the sense of a nanowire comes from these schematics here. We started with a double gate one, with a tall and narrow device, and then if we reduce the fin height, so this is the silicon height, this is the silicon width. If you reduce the fin height, it starts becoming more controlled. It started being controlled by the sidewall gates because you had in the beginning a very thick oxide in the top. But if this oxide is reduced for the same thickness of the sidewalls, you start having conduction in the three gates. So this started to be called tri-gate devices in the past. And nowadays, these tri-gate devices evolved to the name of nanowire. And the idea of nanowire comes because when you fabricate them, they have some rounded corners in the four borders, and becomes similar to a cross section of a wire. When we talk about nanosheets, we have the same structure, but we have also here conduction in this gate, in which you have also the same gate stack in the bottom of the silicon layer. Okay. Well, these devices have been evolved in several ways. Here you see 2 stacked nanosheets. Here you see 3. Here you see 7 levels of nanosheets and their proposers. So IMEC, Samsung, CELT, and so on. So these devices, nanowires and nanosheets. I hope with these examples, I convinced you that several people is interested in evolving these devices for the next technological nodes. Well, but I must say that in the nanometer range, the planar fully depleted SOI MOSFETs also are presenting very attractive technological characteristics and electrical performance. So in the past few years, some companies dedicated a lot of huge investment to evolve these technologies in which you have a single gate controlling, but you have a very thin layer of silicon and a very thin layer of boron oxide. So they also have multiple gate devices. They also have metal gate material. They also have high K dielectric. So the gate stack is quite similar between nanowires and planar silicon-on-insulator MOSFETs. And then a part of our recent work is started to be dedicated to investigate the performance of these devices in the 10 to 80 nanometer and 22 nanometer technological nodes as they are evolving to 10 nanometer technological nodes in the coming years. Okay, so as I told you, the multi-gate MOSFETs can provide good electrostatic control, but this good electrostatic control can also be achieved by thinning the silicon layer in planar fully depleted SOI devices. Okay, so this is the basic idea, is to improve the charge control by the gate and then avoiding short channel effects. So let me then go further with the nanowires. So here you see a construction of the nanowire. I will not insist too much on it because I already told you some information on them. Here you see the remaining part of the boron oxide. You see the silicon layer, and you see the remaining gate stack. But what is important in this picture, these nanowires have an additional etch process that etches a part of the boron oxide before doing the gate stack. So actually, although they are tri-gate devices, because of this omega shape, so here you see the Greek letter omega, because of this omega shape, this region here exposed to the boron oxide is very much reduced, and this device is in an intermediate region between the tri-gate operation and the gate-all-around operation, in which you have stacked layers nowadays. And as I told you in the beginning, the companies are investing a lot to develop these technologies. So these devices are very nice because they have strong immunity to short channel effects, and they are still an alternative for fabrication using the knowledge taken from the FinFET development. In these devices, we can also apply another very well-known technology or very well-known knowledge from the semiconductor industry to improve the carrier mobility, which is the application of strain. So we can build these devices not only in silicon material, but also in silicon germanium material. By doing a combination between silicon and germanium, you can have a material here in the channel. Here you see a cross section of the channel of a nanowire like this one, but in this material, you see here this cross section is perpendicular to the channel. So this cross section gives me the opportunity of saying that at the source and drain of these nanowires and these nanowires, you have some raised source and drain to lower the contact resistance and lower the series resistance. So here you see the cross section of these nanowires, and here you see the perpendicular view. Okay, but what I was talking is by applying silicon germanium material, you can have some strain, and it is now from the silicon technology that the application of strain improves the mobility, both for holes and for electrons, as I'm going to show you in the coming slides. So Using these structures, we can build up tri-gate devices, or we can build up stacked nanowires in which you have a tri-gate device, and on top of that, you have a gate-all-around device. So I'm going to talk about these devices as well during the presentation. So before talking about my experimental data, let me just comment briefly on the motivation for the cryogenic operation. Cryogenic operation is with the semiconductor technology since long ago. First results from operation of MOSFETs in cryogenic environments comes from the late 80s, and they are very much explored over the time. So it was a niche in which what you basically know is that reducing the temperature, we have an improvement on short channel effects for the same technological node, and we know that the carrier mobility is increasing. So these are the basics. When you lower the temperature, these are the improvements. But recently, in the past few years, a boom on the cryogenic operation of several electron devices started. And this boom has been triggered because of the quantum computing. We know that the quantum processor needs to operate in very reduced temperatures, below, let's say, 1 Kelvin. And the first quantum computers started operating with the qubits and the quantum processor in the very reduced temperature range, let's say in the 20 to 100 millikelvin range, or sub 1 Kelvin. Because using a huge set of connections, a huge set of cables, these processors were connected to the classic controller, and the classic controller needed to deal with the error correction, not only for the quantum processing, but also with the thermal noise, with a lot of problems coming from the huge amount of cables or cabling we needed to connect the processor with the controller. But recently, or relatively recently, people came up with this idea. Let's keep the electronics in the room temperature range, but do a part of the control, a part of the readout from the quantum processing using low temperature electronics, placing the electronics in the range between 1 and 4 Kelvin. This idea reduced very much the cost of controlling the system, reduced very much the problems associated with thermal noise and so on. And because of this idea, the boom on the cryogenic operation of several technological nodes, some of them relatively old yet, started. And this is why I would like to position you on the recent interest on cryogenic operation of MOSFETs. So as I already told you about the omega gate MOSFET, so I will not go further in details. So let's see what happens with nanowires. The nanowires I'm going to present you, let me just check the watch. Okay, the results I'm going to present you are initially made for taken from omega gate devices fabricated as CELT. They are fabricated with a thick boron oxide of 145 nanometers. They have hafnium silicate and titanium nitride gate stack. There is an interfacial layer of silicon oxide between the silicon layer and the hafnium silicate. The equivalent oxide thickness is about 1.3 and 1.4 nanometers. We measured devices from long channel down to about 30 nanometers, and the fin height is in the order of 10 nanometers, and we have several fin widths from 10 nanometers up to which are nanowires. Here you see it's marked at 20, but we also have some of 10, I will show you, and up to quasi-planar devices with 10 micrometers, just to check how the fin width influences the device characteristics. And also we have these devices fabricated, as I previously mentioned, with similar device characteristics, but slightly high, slightly tall. The fin height is increased to 30 nanometers in silicon germanium material. And this silicon germanium has this proportion, 70% of silicon, 30% of germanium. In the channel N, we have some source and drain strain as well, depending on the type of the device. It gives a biaxial compression of about 2.1 gigapascal. So you have intrinsic strain in these devices. And by narrowing the fins for smaller than 240 nanometers, the biaxial strain, which means strain in both directions of the channel, perpendicular and transversal to the channel, both the biaxial strain becomes uniaxial, mainly, along the direction of between source and drain. Okay, so we have comparisons between these nanowires with the same gate stack and similar dimensions, which give us some confidence on the results I'm going to present. So let me start with the basics for those which are not familiar on the behavior of these devices when we change them from room temperature here in the right-hand side of this picture down to 4 Kelvin in the left-hand side of this picture. This is a picture of the threshold voltage as a function of temperature. This picture is taken for N-type devices. The SOI ones means unstrained devices, and we have two types here. We have a quasi-planar device with a fin width of 10 micron, and we have a nanowire with a fin width of 15 nanometers. And we have strained SOI material, which means silicon germanium material, also quasi-planar, and also in nanowire configuration with a fin width of 17 nanometers. These are the effective fin widths, okay? And the first thing you can see, by lowering the temperature, for those which are not familiar, we have an increase on temperature. And this increase on temperature, regardless the device you have, this increase due to the temperature reduction is thanks to the Fermi potential increase. So by lowering the temperature, we have an increase in the Fermi potential, and this increasing Fermi potential, as we all know, the threshold voltage is closely related with the Fermi potential, and this is why you see this increase in the threshold voltage. Well, depending on the width, we see also some difference between applying the nanowire configuration and the quasi-planar one. If you look at the variation of the threshold voltage on temperature, you see first an increase, but this increase here in black, I'm referring to the quasi-planar devices, and here in red, I'm talking about the nanowires, the same from here for the strained material. But it is clear from this picture that the variation of the threshold voltage on temperature is higher in quasi-planar devices than in nanowires. And this happens because when you have the tri-gate structure, it increases the coupling of the device, minimizing the variation of the surface potential on the temperature. And that is why when you move from planar devices to nanowires, you have a reduction on the variation of the threshold voltage on temperature. And this works regardless in unstrained material or strained material. So the final information you can get from this picture is associated with the application of strain. The application of strain, basically with the application of strain, the delta 6 value on the band structure of silicon splits in two values, delta 2 and delta 4. And these two values, the main information I want to give you, do not worry with the values, but the most important information is that one of these values has a reduction or a reduced band gap with regards to to unstrained silicon. And that's why, because of the reduction band gap in silicon germanium, you have a reduced threshold voltage, independently if you have a planar structure or a nanowire one. Okay, so I started taking a lot of time just explaining the threshold voltage to give you some flavor of what is happening. Here, excuse me, I will just move back to this slide, and you see the variation of the threshold voltage on temperature. Here you have the linear regression of them, and you see it is in the order of 50 millivolts per Kelvin in nanowire configuration, and it is about 70 something millivolts per Kelvin for quasi-planar devices. So it's quite close here, and here you see some differences, but okay, they are quite close. Here is for PFETs. So basically you see the same results, varying from room temperature down to 4 Kelvin. You see threshold voltage. You see the threshold voltage increase on temperature. So here is the increase in absolute value. These results were, as the previous ones, taken at the low drain voltage, low drain bias. And in this case, we have a very similar fin width of 20 nanometers, and you see quite similar results for the variation of the threshold voltage on temperatures. So basically, if you think on a circuit design or so, you can take a figure or a number like in tri-gate devices, the variation of threshold voltage is in the order of 50 millivolts per Kelvin when you go to cryogenic environments, and when you go to quasi-planar devices, this variation increases to about 70 millivolts per Kelvin. So this is a number that you can keep with you. This number is repeated in different places, and if we look on previous works we did on FinFETs, on tall FinFETs, the result is about 60 millivolts per Kelvin in tall devices. So here you see a slightly reduced variation on temperature, but it is in the same order. So, okay, so this is the basics. So let's move on. In these also basic parameters, let me then accelerate a bit. This is the subthreshold swing. And here I'm showing, as I mentioned it in the abstract of this presentation, I would like to show you not only the basic device characteristics, but also some peculiarities when we expose these devices to lower temperatures. And here it's one of the first peculiarities I would like to show you. This is the subthreshold swing. So for those which are not familiar with this information, this is a log of the drain current. This is the gate voltage at a reduced drain voltage, and in log scale, the subthreshold swing is the slope of this region. So some authors call it inverse of subthreshold swing, but the most important information we got from here is how close to the ideal behavior of a switch the MOSFET behaves. Okay, so this is the subthreshold swing. The minimum theoretical limit is due to the diffusion conduction given by this equation, kT over Q times the natural logarithm of 10. And here you see this straight line, here, the dashed one, which indicates the ideal subthreshold swing. And you see that regardless if in strained or unstrained material, independent if it is very wide or if it is narrow, the subthreshold swing at room temperature is quite close. Here is for NFETs. It is quite close to the theoretical limit, and it remains quite close to the theoretical limit down to about 100 Kelvin or so. Here you see the same results for the PFETs, and you see the same. You see it close to the theoretical limit, down to about 100 Kelvin, and then it starts departing or not reducing the same rate as predicted by the theoretical limit. So when which means when we reduce the temperature, we start doing something like this with curves. So they become steeper. But at a certain level, it is not steeper anymore. You start having problems with the subthreshold swing. So what is happening here? So this, in the beginning, was associated with the interface trap density, because the interface trap density, actually, if you look to this expression, there is an additional term. This is the ideal one, but if you multiply it by the n term, oh, I'm trying to write an n. Oh, thank you. This is the body factor. The body factor increases from the ideal case, which is the unity, to higher values, and it increases more if you increase the effective trap density. But at a certain point, the community started looking at the amount of interface traps to reach this kind of saturation in the subthreshold swing for lower temperatures should be extremely high, unrealistically high. And people started investigating why this happens. So there are two base theories. The most accepted one, it is not closed yet in the literature, but one of the most accepted ones is this here. At cryogenic temperatures, we have low thermal energy for the carriers. And during the fabrication, we have some band tail extensions. These band tail extensions can be at the extensions of the device, but also in the silicon layer. And these extensions can be caused by the ion implantation, by defects occurring during the processing. It is not clear exactly why these band tail extensions take place. But what is clear in this theory is that if the thermal energy is smaller than the band tail extension energy, the subthreshold swing lower limit becomes temperature independent and can be expressed instead of this typical equation, it becomes described by this equation. So you have here the energy level of the band extension and not KT over Q, or the KT term, okay? And M is the subthreshold slope factor, which ideally would be equal to the unity, but it changes also slightly with temperature. But by using this model and changing this with the band tail extension energy, people reached similar values for the minimum subthreshold swing that suffer a kind of saturation in lower temperatures. So this isn't good. So this is not expected, and this is not the best. Depending on the technology, then, depending on the fabrication, you can reach different minimum levels. But the minimum level I generally see is in the order of 10 to 15 millivolts per decade when devices are operating in the order of 4 Kelvin, just to give you a number. Okay, so let me show you another peculiarity, also from nanowires. Jason, please advise me how I'm running on time. I will try to speed up a bit. So here you see the transconductance, the first derivative of the drain current with respect to the gate voltage, and you see at room temperature the transconductance is quite well. Okay, same behavior, regular behavior. You see the beginning of transconductance. This is for a PFET. You see the beginning, and then it reaches the maximum mobility, and then you start having the scattering of the carriers, degrading the transconductance. This is normal. By reducing the temperature, you have an increase in the transconductance on temperature. So this is due to the carrier mobility. This is me of the holes. This is well known. So you see the increase on the peak. But when we enter the deep cryogenic regime below 50 Kelvin, you see two things. The first thing is that, let's say here first at 100 Kelvin. So this is the green one. You're still looking at a very straight or a very flat transconductance. So you have a huge mobility degradation. You see the peak is increasing, but below 50 Kelvin in the deep cryogenic regime, you see a small increase or a smaller increase on the peak transconductance, but you start looking at some bumps. Let me call your attention to the 10 Kelvin curve. Here you see one bump, here you see another bump, here you see another bump. So what are these bumps? This is a peculiar behavior for devices being applied in very small temperatures. Well, when you have a small drain voltage and you have a very reduced temperature, the carriers are quantum confined in two directions, in direction perpendicular to the channel and in direction transversal to the channel. But because of the separation between the bands, you have the subbands field, but you know that the carriers don't like each other because they have the same charge, so they repel each other. So once you have enough energy to fill a certain subband, the carriers in this subband starts interacting each other, and you start looking at some mobility degradation because of the interaction between the carriers in that subband. So this lowers the mobility, and this is why you see this reduction here. But then you increase the gate voltage, you give to the system more energy, and this energy allows the carriers to move to another subband. They populate the subband, which increases the transconductance, but once again, they start scattering each other because they are repelling each other. And then you start looking this bump. And this happens all this time. So this is a peculiar behavior of quantum oscillations in the transconductance, as you clearly see in these experimental data. So these transconductor oscillations are associated with the mobility degradation in the inter-subband scattering, as I previously mentioned. What happens if we increase the fin width, even for lower temperatures? Increasing the fin width, you don't have anymore the quantum confinement. So you reduce the quantum confinement, and by reducing the quantum confinement, the problem associated with the formation of subbands disappear. And this problem, or disappearance of the subbands, can be observed here, will result in very smooth transconductances as you increase the fin width. So you only see the bumps in the transconductance in narrow devices. Okay, this is the first peculiarity I would like to show. This also changes as it is related with the energy. This also changes with the drain voltage. Depending on the drain bias you apply, you can face more or less bumps. So let's start with the 10 millivolt drain bias. And you see in 10 millivolts, where you have less energy, you see more bumps. They are high in number, and they also, you can see 1, 2, 3, 4 bumps, and they are high in number, and they are also stronger. But as you increase the drain bias, you see that these bumps are disappearing. And once you reach, let's say, 100 millivolts, you see almost no bump can be seen, which means the number of bumps are associated with formation of subbands and with the thermal energy, with the energy you provide. So by increasing the drain voltage, you reduce you populate more carriers, and the energy separation in these subbands diminishes, and then because you can populate more subbands and no GM oscillations can be seen. So for higher temperatures, there is no separation of subbands, as I previously mentioned it, and you don't see, even here at low gate voltages, you start not looking at any GM oscillations. Okay, so these oscillations also appear at the capacitances. Once you measure the gate capacitance as a function of the gate bias, let me see how I'm running on time. About 20 minutes, okay, Jason?
Yes, it is okay, Marcelo. It's okay.
Okay, thank you, Gilson. I will then try to speed up. I'm trying to explain a bit in details the things because there are several things to be told, but I will try to do my best. Okay, so you see, lowering the temperature, you see these variations, these oscillations in the capacitances, also associated with the formation of subbands. So you see the GM oscillations are also coincident with some capacitance oscillations, and by increasing the temperature, these capacitance oscillations start disappearing. So you see here the capacitance curve obtained at room temperature down to 5 Kelvin, and you see clearly the oscillations. They are not so strong as in the transconductance, but you start looking. And finally, let me show you also some information about the mobility, but the information about the mobility I will detail a bit more here in this slide. So far I've mentioned to you some advantages of lowering the temperature, some peculiarities of lowering the temperature. So let me move back to one clear advantage, that is the increase of carrier mobility. But one of the questions that raised when we started this study is if lowering one of the strain components in nanowires, if by lowering this strain component, we would lose the improvement on mobility and the improvement on mobility due to temperature. So I'm starting to look here to show you here some results for the mobility. Here are for the unstrained material and here for the strained ones. These are for 25 nanometer wide nanowire, at low drain bias. And you see, in general, that the mobility increases with temperature as expected. So here at room temperature, here at about 10 Kelvin, okay? So you see the mobility is increasing. And by moving to strained material, you see at room temperature an increase of about 61% here. But by lowering the temperature down to 10 Kelvin, you see here the floor of the mobility for unstrained material and for strained one, and you see an improvement of 86%. So that's good news. We still can rely on the improvement on mobility by the application of strain, also lowering the temperature. Actually, lowering the temperature, you observed some additional component on the mobility, some additional improvement on the mobility experimentally as given in this data, which I'm going to explain in the coming slides very briefly. This slide is referring to the component of biaxial or uniaxial one, but the most relevant information in this slide comes in the mobility of the most relevant devices are the narrow ones. Okay, so I will considering my time constraints, I will move on to the analysis of the narrow ones. But the main information here is that the narrow ones. But when you have a wider device, you have larger conduction in the top plane than in the side walls. And because of the top plane is in 1, 0, 0 direction, and the side was in 110 direction, it affects differently mobility for electrons and holes, and making some contribution on the carrier mobility in the medium range of the fin width. But actually for the industry or for the coming circuits, the most relevant information comes from the narrow ones. So I will skip these devices and we will move to these ones where you can have devices with a narrow configuration. So once again, long channel devices, low drain bias, and here you see the carrier mobility as a function of temperature. These curves were extracted using the split CV technique. This is the combined measurement for those which are not familiar. This is a combined extraction between capacitance and drain current curves to observe the evolution of the mobility as a function of the inversion charge. But okay, what you can see in this curve, regardless if you have unstrained or strained material, is that you see the squares have larger mobility, and this is because they are wide, and wide material has larger mobility because the mobility on the top is higher than the mobility in the silos. So in a narrow device, the conduction in the silos is more relevant than the conduction at the top, and because of that, you have higher mobility in wider devices than in narrower ones. Okay, but by looking at the narrower ones, you see that strained material has larger carrier mobility than unstrained ones, and it happens independently if in the narrow or for the narrow or for the wider ones. But looking at the temperature axis, you see some exponential increase of the carrier mobility down to about 100 Kelvin, and then you see a kind of saturation in the carrier mobility, or you don't see the same tendency. In this region down to about 100 Kelvin, you see a power law type where the mobility is increasing in the T over minus gamma law. And if you take the coefficients, the gamma coefficients of these straight lines, you end up with minus 65 for the for the strained material, and minus 808 for these unstrained ones. Okay, so strained, unstrained. Okay, well, so it is given here. Well, first thing to say is that the mobility following the T over minus gamma law is a typical characteristic of a mobility scattering due to phonon scattering mechanism. So in this range, you see a huge contribution of the phonon scattering mechanism, but the phonon scattering mechanism doesn't affect equally the unstrained and the strained material. So to try to get some insight in this region, why there is a difference between the unstrained and strained material, we came over the theory of the phonon scattering. And what happens when you apply strain? As I told you in the beginning, when we apply strain, you have variation in the delta 6 value, which splits into delta 2 and delta 4. And another effect coming from strain reported in the literature is the suppression of the phonon scattering thanks to the delta 2 and delta 4 values. So this suppression of a phonon scattering mechanism is the cause for the reduction in this power law in unstrained material, which is related to the phonon scattering. As you have the phonon scattering component strongly in unstrained material than in strained one, this is the reason where you reach the higher coefficient for the carrier mobility. So this explains why the mobility increases in this region and why it increases differently in the strained and unstrained material. But what happens in this region? why the mobility increase is attenuated in the lower range. Well, by looking at the mobility components using the split-sieve technique, it's possible to isolate the component associated with the phonon scattering and also other components. And in this region, where we extracted the effective mobility, we start suffering some surface roughness, limiting the carrier mobility. So the influence of surface roughness on the carrier mobility becomes higher, and because of that, we obtained this reduced carrier mobility increase in this range. This happens not only for NFETs, as I showed you, but also for PFETs, as I'm going to show you here in this slide. Okay, so this is some more details about the influence of surface roughness on the effective carrier mobility, but because of for the sake of time, I will not go into much details. But it proves you have phonon scattering here, you have the surface roughness. It demonstrates that the influence of the carrier mobility due to the surface roughness is the cause at higher inversion levels, is the cause of this degradation or this smaller increase in the carrier mobility on temperature. Well, just a final word on nanowires, and then I will move on to self-heating of planar devices, which I think it's more of your interest than to talk about this, on stacked devices. Does it affect the circuit operation? At the end, when we move from room temperature down to cryogenic regime, does it translate in some change in circuits? Okay, I will just say a brief word. The transconductance to drain current ratio changes, and by changing it, here is you see the weak conversion region, and here you see the moderate one, and here you see the strong conversion region. So it does affect, and it does translate in changes in circuits. It changes the transconductance and also the output conductance. You see here in this curve, the closest symbols refer to transconductance, and the open circles refer to output conductance. But the main message here is that both the transconductance, because of the carrier mobility, and the output conductance, not only because of the carrier mobility, but also because of the channel length modulation due to drain bias, these data were obtained at high drain voltage change. And for example, if you look at the intrinsic voltage gain of the transistor, you see the voltage gain slightly changes on temperature. You see here the voltage gain of nanowires, and here you see the voltage gain of quasi-planar devices, and you see also the early voltage in the other side, and the high trend side x-axis, and you see that you see some change in the intrinsic voltage gain of the device. So it does affect the operation, not only digital, which is more popular, I'd say, popularly now, but also in analog design. Okay, I will skip the stacked nanowires, but the main message for the stacked nanowires is quite similar to those given for the planar nanowires. You see some slightly different scattering mechanisms, but these devices operate with some quite close subthreshold swing. We see some differences in the threshold voltage. The variation of threshold voltage in stacked nanowires is in the same order than for unstacked ones, but I will not go too much in details in these data because of the sake of time, and I think it is more of your interest to keep in touch with the data of planar SOI devices, which are one of the enablers, as I told you in the beginning, for the coming future technological nodes. We can find commercially available 22 nanometers, 28 nanometers technological data and technologies to buy. And people is evolving these planar fully depleted SOI devices to the 10 nanometer technological node. So it's a nice contender. They are already developed for the 14 nanometer. This has been presented last IEDM, and they are thinking to evolve it. They see potential to this technology to evolve it to further technological nodes. I'm sorry, some of the slides here are in Portuguese. I took them, but forgot to translate some of the parts. I really apologize. But these devices were fabricated in ST Micron, and they follow a quite similar technology to that offered commercially offered and also being offered by GlobalFoundries. Okay, so you have a silicon layer of 7 nanometers. You see the raised sources and drains, and I will show you data from 2 different gate oxides, 1.1 effective gate oxide thicknesses, 1.1 nanometers, which is the low VT devices, and the 3.2 thick gate oxides, which are the thick ones. Okay, we changed the channel length, we changed the channel width to investigate the influence of these devices, but because of the time, and I want to left some time for discussion, I will focus on just some of them to give you the flavor. To obtain these devices, oh, I'm sorry, this is completely in Portuguese, but to obtain the data for these devices on operating self-heating, I used the so-called gate thermometry. And the gate thermometry relies on the idea of, let me show you, I will skip these initial ones, I come back later, but this is the idea. Basically, you see 2 gate electrodes and the electrodes of the MOSFET. So you have a regular MOSFET, but together with monitoring the device temperature while together with biasing the device during the regular operation by applying drain and source voltages, I also applied a DC gate voltage into the gain, but coupled with the DC voltage, I have some AC signal flowing in these 2 electrodes of the gate. And this AC signal is monitoring the gate resistance. So the idea is you increase the temperature of the silicon. This silicon is closely connected or coupled with the gate material, because you have here the gate oxide here and here the gate oxide. And here you see the higher thermal resistance, which is given by the buried oxide, which is about 100 times larger than the thermal resistance of the silicon. So you heat up this silicon layer, and then you heat also the gate metal. And by monitoring the gate metal, you have a clue about the temperature that the silicon is by looking at this resistance. So to do this behavior, to look at this behavior, we have some special apparatus. I will just show you in a while. But the idea is first to have with the device off. You have to monitor the resistance over the temperature. And then by having this calibration curve over the temperature, you then start looking the temperature of this region when the device is on. When the device is biased and heated up. And then by looking at the calibration curves, you have a clue, you have an idea about the temperature. So just about the apparatus, you have the DC bias provided by an Agilent equipment or B5000 device and so on. And then you have an SLR meter in which you bias the AC signal in the 2 gate contacts, and then you see the regular biasing of the MOSFET. I'm sorry once again, because this slide is in Portuguese. So you see here the basic device characteristics. I'm not going to stress very much this information. Essentially, you see the same as I shown in the previous results for nanowires. By reducing the temperature, you have an increase on the threshold voltage, so reducing because of the Fermi potential, and because of the thermal temperature reduction, you see a reduction of the subthreshold swing. Here you see the theoretical limit, and you see that at certain point, you see a kind of saturation in the subthreshold swing, independently on the gate oxide thickness. Okay, you see that thicker gate oxides have less traps, and the body factor is smaller, and then because of that, you see smaller subthreshold swing. Okay, here's a typical drain current as a function of gate voltage. So you see it in log scale and in linear scale, and you see the steeper subthreshold swing when you go to cryogenic regime. You see a very regular increase on temperature, and then you see a kind of saturation because we increase it very much, the gate voltage, but you see a kind of saturation in the drain current in linear regime. These are these curves are in the log scale, and these are in the linear ones. And you see here the temperature, whether the current is independent on temperature. So if you bias the device here, you see the current is not changing very much because of the temperature. So you see a very close connection here. Well, by increasing the temperature, we see an increase in the mobility. So these are the carrier mobility data as a function of temperature obtained by split CV. So reducing the temperature, main message. You have an increase in the carrier mobility, a very nice increase. You see about 4 times larger mobility at 4 Kelvin with respect to the mobility at room temperature. So this is nice for long channel devices, okay? So these are for the low threshold voltage devices, but it also happens for the high threshold voltage devices. But okay, this is for the load. This is a summary of the data I've previously shown, but the first data is for long channel devices, and this is for very short channel devices with a mask channel length above about 30 nanometers. So essentially the same. Increase of threshold voltage, reduction of subthreshold swing, saturating in the order of 15 millivolts per Kelvin per decade, I'm sorry, and the same for narrower devices. Okay, so by changing the channel length, you see essentially the same. And also, due to the channel length reduction, there is a reduction in, there is an increase, I'm sorry, in the transconductance, as you see here also. Well, the same for thicker gate oxide, so I'm not going to details in this data because it is very much close, very much similar to the previously shown. So let me show you then some information about the self-heating, which is most important thing. Here you see what is known about the gate thermometry. So by looking at the power, it is known that you have an increase in temperature due to self-heating. This can be obtained by experimental data. This can be obtained by calculation using a simple model. And I'm going to show you in details the influence of the thermal resistance and the variation of temperature for experimental data as in this curves that I'm going to show you very briefly. So this is the calibration curve, the gate resistance as a function of the ambient temperature. This can be obtained changing the environment temperature and then making this in these sets of measurements by varying the temperature, the environment temperature, and you have this behavior. And in this behavior, you can see that below 50 Kelvin or so, you see some saturation of the gate resistance. The gate resistance becomes less accurate to monitor the temperature. This is a problem to be solved. But okay, this is the technique we are using. And that by looking at the thermal resistance, by applying high voltage into the device for a very short channel transistor, you see this thermal resistance behavior. And by using the thermal resistance for the device, we can calculate the increase of the temperature into the device, depending on the environmental temperature and depending on the power the device is dissipating. So you can see by the data of the thermal resistance that for temperatures smaller than 100 Kelvin, you see a sudden increase in the thermal resistance of the device. And this increasing thermal resistance translates into a higher thermal increase with the power when we are in the deep cryogenic regime. Increasing the temperature or the environmental temperature, we see with the power a reduced increase on the device temperature. But some information from this curve is very intriguing. For example, if you bias the device, and these are for experimental data, if you bias the device, let's say, below 1 millivolt in terms of power, you are with the device you are with the device operating in the 4 Kelvin range. This is the environmental temperature. But effectively, effectively you are having, let me come back once again, here, yes. Effectively, your device is not operating at 4 Kelvin. Because of the self-heating, your device starts operating at about 50 Kelvin. With this very small power. If you increase the power, the device temperature suddenly reaches 80 and 100 Kelvin and so on. So there is a huge effort to put the device to operate in 4 Kelvin. But because of the self-heating, you see it is happily increases to tenths of Kelvin. And this increase is very sudden for when the device is in below 100 Kelvin environment. This can be seen independently on the channel length, but of course, reduced channel length dissipates more power. And because of the reduction in the channel length, you see higher self-heating, okay? Independently on the environment. So this confirms the data for several channel lengths. These are for PMOS data, these are for NFET data, and if I change the device width, I see the same. This is the calibration curves, and I see here the influence of the channel width, but the information is pretty much the same. When you increase the device, when you put the device to a cryogenic regime, you see the thermal resistance departs from the thermal resistance from the boron oxide, which is given in this dashed lines, and starts seeing a sudden increase on the thermal resistance. And this sudden increase in the thermal resistance is closer to the increase of the thermal resistance of the silicon, of the synsilicon, and not anymore of the boron oxide. Well, this is quite intriguing because this experimental data is saying that in the moderately higher temperature range, the dissipation is being limited by the boron oxide. But in the cryogenic regime, the dissipation is being limited by the silicon itself, by the thermal resistance of the silicon. So which imposes that the dissipation is happening or is not trying to happen anymore in the boron oxide to the silicon in the bottom of the wafer, but maybe in the extensions and to the source and drain contacts. So this is under investigation by several groups and by ourselves as well. If you change the channel length, you see the same. You see the tendency of the thermal resistance moving in narrower devices to the silicon region and not in the boron oxide region, okay? And if you have more transistors in parallel, basically you see the same temperature increase that I've previously demonstrated you in a single device. But when you start having multi-devices in parallel, and these we made to see how it affects the operation, basically you see the same behavior, but putting several devices in parallel, you have a confinement of the heating, and this confinement of the heating results in higher cell heating at the same power than if you have a single device. But okay, these devices are isolated, each one, but the shallow trench region between these silicon layers confine the heating and make these devices heat up in higher value than in a single device. But okay, I apologize because I extended slightly my time, but very straight conclusions from the observations. I demonstrated you some peculiar data on putting these devices in cryogenic environment. These peculiar behavior are generally associated with transconductance oscillations in the nanowires that appear heavily because of the formation of subbands in the conduction band and the quantum confinement due to the very reduced dimensions. I demonstrated you oscillations in the capacitances as well, and I demonstrated you that silicon germanium material can provide mobility enhancement higher than the unstrained material in nanowires, which are good news. Well, for the fully depleted SOI devices, I demonstrated you the operation of devices down to 30 nanometer channel length, and I've demonstrated some huge self-heating occurring when these devices are operating in cryogenic environments. I know this is a large amount of data, and because of the time, I could not discuss too much all the data, but the main information I would like to pass you I highlighted during the information. The operation in cryogenic environments in general generates device heating, and this device heating, for example, in SOI devices, is quite important. You can reach tens of Kelvin, even putting the device to operate in 4 Kelvin range because of the intrinsic heat of the device. Well, a word about self-heating in nanowires. There is very few information. I cannot tell you because we are working on to obtain it. Well, with that, I thank you for your kind attention. Let me then exchange my screen to this one, in which I'm seeing you something. And then I will be happy if I can answer you briefly some information. Otherwise, you can contact me by email, and I will be glad to provide you additional information because of the time. Okay, thank you very much for your kind attention and for inviting me to give this presentation.
Thank you, Marcelo. Thank you so much for the talk, really great talk and very comprehensive. And we have a few questions. The first one, let me see, I think you can see it there, is have a little question. Why some papers use VGS equal to 50 millivolts to measure the IDS VGS, but some people use VGS equal to 40 millivolts?
Oh, there is no special reason. The idea is to put the device in saturation just in the beginning of the curve and then migrate to linear region to check when you have the overall channel in inversion. So you are in linear region, so you want a small drain bias. In the past years, people use it 100 millivolts. Nowadays, people using 25, 10 millivolts, 40, and 50. In our case, we started, I have to be very honest with you, we started using 40 millivolts. In the beginning, we used 25 and 50. But we started using 40 millivolts because people in CELAT use 40 millivolts and 900 millivolts. And then I started measuring with these voltages to compare the experimental data we have here in Brazil with the experimental data that we have there in France. So there is no special region. The basic idea is to have a very small saturation region and the overall linear region to look at the carrier mobility degradation over as a function of the transversal electric field because of the perpendicular electric field, because of the gate voltage.
Okay, thank you. We have another question. What is the possible maximum self-heating effect of a device?
Nice question. Well, I will answer you based on the experimental data I have. Okay, but this is something that is in discussion on the community. So let me go to the temperature here. Yes, this curve is quite intriguing. I can show you in PFETs or in NFETs, you will see the same. You put the device to operating 4 Kelvin range. And we generally want to have a very high, the highest current available in the device. So you want to increase the power. Okay? We want to increase the power. But, okay, you cannot increase the power because you heat the device. You put it to operate. In 4 Kelvin environment, you reach this power, you reach this temperature. So what is the advantage of lowering the temperature? If you will bias the device in this range. This is discussion. People is studying how to deal with a smaller power, trying to minimize the power to not generate heat. But okay, to give you a straight answer, experimentally biasing the device in these devices are quite short ones. Okay, we reached temperatures in the range of 150 Kelvin higher than the environmental temperature. Okay, by lowering the temperature, you increase the temperature. So you asked me about the maximum. Here you operated at 300 Kelvin plus 40 Kelvin. So we are talking about 350 Kelvin, effectively, in these experimental data. So at room temperature, we can reach about 40 Kelvin heating up the device. You increase the power. At 4 Kelvin, you heated up the device about 160 Kelvin. But you see, the maximum temperature reached depends on the environmental temperature. But the bad thing you have with the self-heating is associated with the fact that you bias the device, you put the device in a certain temperature range, but you cannot hold it for long if you increase too much the power. I don't know if I answered your question. Otherwise, please, I can come back
yes, I think
to that.
So. Yeah, I think you answered. We have another question here. Is air gate equal to metal gate resistance or
No.
high K plus metal gate?
No. High K plus metal gate. It's a parallel association. Yes. And, in general, yeah, it's a parallel association, but we have the effective resistance, and you realize that the metal gate layer is very thin. So most of the resistance is dominated by the, you asked about the resistance of the gate, and I was thinking another. Sorry, let me address your question again. I'm sorry. You asked if the metal gate is composed, the resistance is composed by the high K dielectrics and the metal gate resistance. Sorry, now I understand better your question. No, it's just the metal gate. There is no influence of the high K dielectrics on the metal gate. If you look at the conduction, if you look at the gate current, which could influence the resistance you measure, you are just monitoring. There's very small gate current, so you are just monitoring the resistance of the gate metal. So this is for sure. Of course, you can have some capacitance coupling. When you apply the signal, you can have some capacitance coupling in parallel between the capacitance of the metal gate layer and the capacitance of the insulator itself. But this is why we apply an AC signal to lower the capacitance contribution while measuring the gate resistance. So we try to minimize the capacitance impedance, lowering the frequency, and look only at the resistance impedance of the metal gate. So you asked about the high K, and I was thinking about the metal gate material and then the polysilicon you have on top of that. And I was about to say that the metal gate is very thin. The metal gate is about 5 nanometer thick, and the polysilicon is in the order of, it can reach 30, 50, 80 nanometers thick. So the resistance of the polysilicon is smaller than the resistance of the metal gate itself. But what we monitor by measuring the gate resistance is the effective parallel resistance of the metal gate layer and the polysilicon layer. Sorry for my confusion, because I was thinking one thing and said the other thing. And you asked another thing, sorry.
Thank you, Marcelo. And we have a last question here. Do you see the cryo regime being commercially viable? By viable, I mean, can we benefit from this, or would it be limited to the industry only?
Oh, nice question. But this is a tough one. Well, most of the cryo regime is now being focused on the operation of quantum computers, which is limited by the cost, is essentially limited to industries. But I must say that we can face cryo regime in some aviation applications, in some aerospace applications. Depending on the application, we can have cryo regime, not necessarily reaching the 4 Kelvin or sub 1 Kelvin regime. Okay, so if by viable you're meaning personal computers, I think we are far from that. They are far from that. We are nowadays far from that. If you by saying viable, you are meaning better processing machines in data centers or so on. I think it is really viable and is one of the enablers for the future of CMOS applications. And of course, not by saying this, I'm not specifically talking about quantum computers. I'm also saying about regular computers that we need to operate in smaller temperatures to improve the carrier mobility and improve the speed of processing. And of course, as I said in the beginning, yes, we can be benefited about cryo computers in the near future, which is the main focus of several groups nowadays, including ourselves. I don't know if I answered your question, Enrique. Please come back to the question with in private if you want, and we can discuss. This is a nice discussion.
Okay, thank you. It seems there are no questions anymore. I would like to make a last question, if possible. Marcelo,
of course.
If you go to Enrique's Kessler said yes, that you did answer his question.
Thank you, Enrique. It's a pleasure.
Regarding quantum computing, what is more important? The gain that you get by operating at very low temperature. I mean, if you are at 4.2, but the device is, let's say so, possibly not at 4.2 due to self-heating, and you lose performance. That's one issue. But the other issue is this really relevant, or is more relevant that for quantum computing, you do not heat up the quantum computer core, where you have the quantum bits and so on. So it's really that important that you get that performance surplus by operating at low temperature, or it's more important that you do not interfere with the quantum computing core?
Well, let me see, because your question has to be answered in different aspects. First of all, nowadays there is no, the idea is not to have the control and then the quantum unity in the same chip, monolithically integrated, which means I heat up one part, but the other part will, as a consequence, also heats. The idea is not to have that in mind. The idea is to have the quantum part, the quantum core, in the smallest temperature possible. Okay, depending on the qubits, the technology of the qubits, so which has been in development. But okay, once you have the quantum, the qubits and the quantum core well controlled and everything, you need to have DA converters, you need to have data error correction, and so on. There is several experimental demonstrations that you can be benefited by having these parts of the circuit in the 4 Kelvin range, in comparison to the room temperature operation as in the past. And the main idea, mainly because of the scaling, maybe because of the huge amount of data you may need and the huge circuits you may need to control the qubits and the quantum core. So yes, there is an advantage. But what people is doing today is not only investigating these enablers for the most advanced technological nodes in real as applied nowadays, which are the FETs, the nanowires, and the fully depleted SOI, which are strongly suffering from self-heating. But the people is also investigating some, let's say, relatively old technologies that doesn't have the Bourdieu to use in these control units at 4 Kelvin. The bad news from experimental data that I've just shown you, and which is being published very recently, is that suddenly the heating started being limited, the heating dissipation started being limited not only by the substrate, which was the killing problem for the SOI technology, but as I've briefly demonstrated, the heating is being evacuated from the device through the source and drain regions. And bulk devices also have sources and drains. But even dealing with the self-heating, there are several circuits being demonstrated in literature very efficiently operating at 4 Kelvin range. The authors don't rely on the temperature. They try to do the design temperature aware and make the design efficiently supporting the temperature variation, and they succeeded on it in these DA converters and these analog data, which I've recently seen in literature. So although the huge effort, just to address finally your question, Gilson, although the huge effort, there are advantages on putting the CMOS logic and the correction systems into logic and analog parts into the 4 Kelvin range. So there are advantages on that.
Okay. Thank you very much. Thank you very much.
Thank you very much for questions.
Yeah, yes. And I think there are no more questions. The people that did ask the previous question, thank you, and I think you did answer the question. And if not, as you said, they can get in touch with you.
Yes, please, do not hesitate.
Yeah, and if you have more questions, you can also please get in touch to Marcelo Pavanello. So thank you really very much for the really very nice talk, and I did learn a lot. Thank you.
Thank you very much.
Gilson. All the other people also did learn a lot. And yes,
thank you. Thank you quite so much. And if you want, any of you, please let me know by email. Any information, comments, questions, criticism, it's all welcome. Just let me know. Okay? So with that, let me then say goodbye to you all. Thank you for your very kind attention. Thank you once again for the invitation, Gilson. And Okay, see you soon.
Thank you, thank you. Yes, thank you so much. And I'm finishing the live streaming now. So thank you, everybody. See you next time. Bye bye.
Stay safe. Bye bye.
Stay safe. Bye bye.